Hello everyone, welcome back. There are some problems in physics. On the surface, it may not seem like there is much, but if you go in depth, we get to learn a lot. So I'm starting a new series to discuss those kind of problems. So these are the problems that make you really think and stretch your brain, right? So these videos will be geared mostly towards rank booster and JEE advanced. In this video, I'm going to discuss Krotov 1.5, that is from this book. Alright, this is a problem statement. Two bodies move in a straight line towards each other at initial velocities v1 and v2 and with constant accelerations a1 and a2 directed against the corresponding velocities at the initial instant. What must be the maximum initial separation L max between the bodies for which they meet during the motion? Alright, so this is my object 1, this is my object 2. Initial velocities are towards each other and the accelerations are directed against the corresponding velocities. So this is going to be a1, this is going to be a2. All right, so this is a velocity this way and acceleration is opposite. So it's going to go like this, stop at some point and then come back. So let me call this S1 max. Similarly, this is going to go, stop at some point and then go back. So let me call this S2 max. So as you can imagine, we are going to use v square minus u square equal to 2a dot s. This is dot product, right? Because we know everything here except s. So if I apply it for this one, finally it's going to come at rest. So 0 minus u, the initial velocity is v1, v1 square is equal to 2, a magnitude is a1, this magnitude is s1 max. A dot s is as cosine theta and the angle between s and a is 180 degree. Cosine 180 degree is -1. Whenever you see they are opposite, actually you can straight away write -2 a1 s1 max, but just to be very clear, now to simplify this negative and negative will be positive. So this will give me s1 max is equal to v1 square by 2a1, right? Similarly, I can write the exact same thing for this and I will get S2 max V2 square by 2A2. All right. Now I want L max. So let me start here. L max. So the maximum distance so that they come like this and touch and then before they go back is going to be, this is maximum and this is maximum, right? So this is going to be S1 max plus x2 max, right? Now if I substitute, so L max is going to be this plus this and I'll take half common. This is v1 square by 2a1. Actually I already took half here, plus v2 square by a2, right? So this is what I get. Seems like I should also be able to solve this problem using relative motion. So let me try that. So this is my body 1, this is body 2, this is v1, a1, v2, a2. I will solve this from this frame of reference, so I'll bring it to rest. So I want to write down the relative velocity and acceleration for this case. So relative velocity of 1 with respect to 2 is by definition velocity of 1 minus velocity of 2. So this is going to be the relative velocity of this with respect to this is going to be v1 minus v2, v1 minus v2. Similarly, acceleration is going to be a1 minus a2. And now we can use v square minus u square to 2a dot s. So essentially this is going to go like this, touch, and when it comes to rest and then come back. So this is going to be my L max, right? Okay, I'm going to come at rest here. So there's going to be 0 minus u square is v1 minus v2 square to a dot s. So this is my direction of s and they are again opposite. So it's going to be 2, A is going to be A1 minus A2, S is going to be L max, and cosine 180 degrees negative 1 like last time. So negative and negative will be positive. So this gives me, I'll write it here, L max is going to be V1 minus V2 square divided over 2 A1 minus A2, right? So this is what I get using relative motion. Okay, let's check with the previous answer. This is what I'm getting here, V1 square by A1, V2 square by A2, and here I'm getting this. No matter how I solve the problem, I should be getting the same answer, right? But clearly this and this are not the same. So which one is right? Which one is wrong? Actually, both are wrong. So this is a trap. The way I have solved this is a trap. This happens to be a special case. I'll talk about it later. Now this is also a trap. This is plain wrong. Okay. Now let me do the correct way. Before that, let me call this solution 1. Solution 1. This I'll call solution 2. Okay. So this is going to be solution 3. I'm still going to use the relative velocity. So I have, this is V1, this is A1, A2, and V2. I'll bring this to rest. I'll write the relative velocity and acceleration for this. Okay, so V2 or V1 with respect to 2, because 2 is at rest, I want to compute the relative motion of this, is V1 minus V2. Relative motion of 1 with respect to 2 is velocity of 1 minus velocity of 2. This is by definition. Now let's try to write this correct way. So V1, let me call this direction as I cap, right? So V1 is going to be the magnitude V1 I cap minus V2. V2 is going to, the magnitude is V2, but it is in the negative I cap direction, right? So that is negative I cap, right? So this is going to be V1 minus and minus plus V2 I cap direction. So that is going to be V12. So if I note that as the positive direction, so the magnitude is going to be V12 is going to be V1 plus V2. V1 plus V2, right? This is the mistake that I had made earlier. Instead of writing V1 plus V2, I had written V1 minus V2 just by looking at this formula, right? But I didn't take the direction into account. That's where I went wrong here. That was a silly mistake. Okay, similarly, so this is going to be A1 plus A2. Now it is straightforward. So this is going to go like this, come to rest, and then come back on the same line, right? So, and this is going to be L max. So I'm going to use same V square minus U square is equal to 2A dot S. V is going to meet here when it comes to rest, so that is going to be 0. Minus U square is V1 plus V2 square. Your 2AS. A and S are directed opposite. So 2A is going to be A1 plus A2. S is going to be L max. And then cosine 180 degrees negative 1 like before. So this gives me, this negative 1 and negative will become positive. So that gives me L max. I'll write it here. Is going to be V1 plus V2 square over 2 A1 plus A2. So this is the correct solution. So here is a $1 million question. How on earth am I supposed to know that the answer that I got previously is wrong or right? Because during the exam, when you are working under time pressure, it is not very uncommon to fall in this trap or this trap, right? So how on earth I'm supposed to know that the answer is wrong. Of course, I have a answer for that, and that is listen to the whisper of expressions. This is very, very important, right? Remember, expression is called an expression because it's trying to express something, right? So we have to listen, we have to try to listen to what it is trying to whisper, what it is trying to tell. And this is not something very abstract. There are three very specific things that I try to listen to every single time. And that is, first thing is unit, is about what it is trying to tell you. Let's say if you're trying to find a distance, is it talking about a distance or something else, right? Second is limit. Is the expression that you got, is it behaving the way it is supposed to behave, right? And then symmetry, is it symmetric with respect to some of the variables? So these are the three very specific things that I check, and this is going to be actually your secret to being very confident that the expression that you got, the derivation that you made, is right or wrong. And again, so this is not something very abstract. I will talk about in detail in the next slide. All right, we derived three solutions earlier. I have copied those here for convenience, solution 1, 2, and 3. Now we will try to listen to their whispers. Let's first do the unit. Remember, it is asking us about the maximum separation. So it is asking us about a distance. So let's check if this is telling us about a distance or something else, right? So v square, that is meter per second square, of that is meter squares per second square, divided by acceleration is meter per second square. So second square cancels, meter 1 cancels, so this is in meter. So this expression is indeed telling us about a distance, so this checks. Similarly, you can also make sure that these two also check for this. Now let's do limit. When v2 is equal to 0 and a2 is equal to 0, so this object is at rest and this is just going, so I should be able to get a finite result, right? But if I put v2 is 0 and a2 is 0, this is 0 by 0, this is not defined, so this cannot be the correct expression, so this fails for this check. So then this is not the correct solution, right? So this again is a trap, and this was a special case. This works for a special case, we'll talk about it next. Now let's now check this. When v2 is equal to 0 and a2 is equal to 0, that means this is 1, this is 2, this is at rest. So this is v1, this is a1. Now if I apply v square minus u square is equal to 2a dot s, you can verify that you should get the L max. This is, if this is L max, that should be equal to v1 square by a1, right? So this is a very simple derivation. Now if I put v2 is equal to 0 and a2 is equal to 0, v2 is 0 and a2 is 0, I get v1 square by 2a1. Actually I should get a 2 here. Remember, v square minus u square is equal to 2as, so there should be a 2 here, and I get the same thing here, v1 square by 2a1. So this checks. This checks. How about v1 is equal to v2 and a1 is equal to a2? So if I put v1 is equal to v2, this is going to be 0. a1 is equal to a2, this will be 0. 0 by 0 is again not defined. So this fails. This limit check, right? So again, this cannot be the correct answer. Again, this was a trap, silly mistake, and this is simply wrong. This is simply wrong, right? Now let's check the last one. Now for v2 is equal to 0 and a2 is equal to 0, we should get this, remember. So if I put this 0 and this 0, I do get v1 square by 2a1, v1 square by 2a1. So this checks for this. Now if v1 is equal to v2 and a1 is equal to a2, so these are the two objects. So this is v2, this is v1, this is a1, and this is a2. Now if v1 and v2 are same and a1 and a2 are same, so from symmetry, they should meet right at the center, right? When it travels and it comes to rest here and comes back, so they should meet right about here, at the center, right? When they come to rest. So in that case, you can actually, this is again a very simple case to derive. You will see that the answer will come to, so this distance is going to be v1 square by 2a1, and this is again going to be v1 square by 2a1, and then if you add it up, you should get v1 square by a1, right? So that should be the L max, right? If I put now v1 is equal to v2, so this is going to be, 4 v1 square by 2 and 2a1, so that is 4a1, 4 cancel, v1 square by a1, v1 square by a1, so this checks, right? Now symmetry, there is not too much about symmetry here, but one simple thing that I wanted to bring it up is I named this as 1 and 2, but I could have named this as 2 and 1, right? So it should be symmetric with respect to 1 or 2. This expression is symmetric, so this checks for symmetry, but this doesn't. Like a1 minus a2 is not same as a2 minus a1, right? So this again does not check for symmetry. Here 1 and 2, if I switch, it checks, right? So as you can see, right, by listening to their whispers or what it is trying to express, I can be very confident now that this is the correct answer, right? So this is the secret of knowing when you come up with an expression. This is the secret how you can be confident that your derivation is right. All right, I keep saying that this is the correct solution and this is only a special case. So let's talk about that next. So this is the general solution. I have copied it here, and this is a special case. Now recall how I arrived at this expression, right? So this is object 1, this is object 2, this is v1, a1, v2, a2. I said, this goes like this, comes to rest somewhere here, and then it returns, and I called it S1 max. Similarly, I said this comes here, comes to rest, and then returns. I call this S2 max. And I assume that, they're coming, and they come to rest when they meet, and then they go away. So they both are coming to rest when they meet. So they're coming to rest at the same time, right? And I use v square minus u square is equal to 2a dot s. There is no time in there, right? So we have to bring that time in. And for them to meet at the same time, I can use v is equal to u plus at to find out the relationship, right? Now here they come to rest. So for object 1, 0 is equal to v1, a is in the negative opposite direction, that is minus a1t. So this gives me t is equal to v1 by a1. Okay, similarly, if I apply the same equation for v2, I will arrive at t is equal to v2 by a2, right? So by assuming that L max is equal to S1 max plus S2 max, this is what I did earlier. So by doing this, I'm inherently assuming that the time is the same. That means v1, I'm inherently assuming that v1 by a1 is equal to v2 by a2, right? So this is the more general solution, and if you use this condition here, v1 by a1 is equal to v2 by a2, you should get back this expression. I will leave that to you as an exercise to check, but I'll give you a hint. Just try to express a1 in terms of the other three, and then try to substitute that here, also substitute that here, and this should lead to an expression, and this should lead to another expression, and this should be the same. Again, I will leave that to you as an exercise. All right, I'm not quite done with this problem yet. You see, during the exam, you will be under tremendous time pressure. So what if the best approach does not occur to you immediately? Like, for example, in this case, if you use the relative velocity, relative motion, and then v square minus u square is equal to 2as, You can solve this problem in 10 seconds, no problem. But there is another commonly used equation in kinematics, that is S is equal to ut plus half at square. What if you start using this? You should still be able to solve this problem, right? So let's try to do that. This is a, b, this is 1, v1, and this is a1, this is v2, and this is a2. So let me call this displacement of 1 as s1 and displacement of 2 as s2. So let me write down this equation for both. I'll do it here, or let me do it here. S1 is equal to ut. V is in the same direction as s, so it is going to be v1 t plus half. A is in the opposite direction, so minus a1 t square. Similarly, I'll write down for 2. The s2 is in the same direction as v2, so v2t plus half. Again, a is in the opposite direction, so negative a2 t square. All right. Okay, now what I want is, let's say the separation between these two, this separation, let me call it L. I don't know if it is L max or not yet, but let me call those separation L. So this separation is L. So what I want to do is enforce this S1 plus S2 to be L, right? So again, I don't know whether this is L max yet or not, but what I want to do is I want to enforce S1 plus S2, the displacement of 1 plus 2, to be the separation between the two objects at the initial instance, so that I know that they met, right? So if I do that, L is going to be equal to S1 plus S2, so I'll add it up, so that is going to be V1 plus V2 t plus half. I'll take the negative sign outside. Half a1 plus a2 t square, right? All right. So this is what I get, and somehow I want to try to solve this equation. Now notice one thing here. If I used the relative motion, right, I can get this expression straight away, right? S, the total displacement, or the relative displacement L is equal to the relative velocity, which is going to be v1 plus v2, we have seen that earlier, plus half a. A is going to be, a is in the opposite direction, so that is negative a1, negative a2, negative I have taken common, and t square. So this, keep that in mind. You can get to this straight away using the relative motion. All right, so now let's try to solve this. So I have copied that expression, the earlier one, this one here. Actually, what I have done is, let me try to rewrite this. Like, I bring it to the left hand side, so that is going to be half a1 plus a2 t square. If I take this to the opposite side, it will be negative v1 plus v2 t. L is already here, plus L. This is going to be equal to 0, right? All right, so this is the expression I will be working with. Here I'm copying this just to the other slide. Half a1 plus a2 t square minus v1 plus v2 t plus L is equal to 0. So L is the separation between the two objects. So by writing this, combining this, what I'm enforcing is that at some time t, let's say they meet. I don't know the time yet, right? Now, if I knew the time, I can find the length, but I don't know the time. I'll try to solve for the time. Now notice that there are two unknowns here, time and length, right? It is quadratic in time, but it is linear in L. and I want to find time. So let me try to remind you the general quadratic equation, that is ax square plus bx plus c is equal to 0. So this is general quadratic equation, and solution for this is given as x is equal to minus b plus minus square root of b square minus 4ac by 2a, and this value here is called the discriminant d. So the discriminant is basically b square minus 4ac. Now this discriminant dictates whether there will be any real solution or not, or for example, if d is less than 0, right, the square root of a negative number is imaginary number, so there will be no real solution. If the discriminant is 0, right, so this part is 0, so there will be one solution, real solution. If the discriminant is positive, there will be two solutions, one corresponding to the plus, one corresponding to the minus, right? So let's keep that in mind. All right, so let me try to write down the discriminant for this. D is going to be b square minus 4ac. So that is, b is this, so this is, for me, this is a, this is b, and this is c, right? So d is equal to b square is the negative square is going to be positive, so that's fine. v1 plus v2 square minus 4ac. 4a is going to be half a1 plus a2, and then c is going to be l, right? So this becomes 2, so this gives me again d is equal to v1 plus v2 square minus 2 a1 plus a2 l. Now think about it for a moment. The solution for the time t, right, depends on the coefficients, obviously, right? Now, and the coefficients dictate when they will meet, if they will meet or not, and if they do, whether they will meet one time or two times. So this is a quadratic equation, so maximum they can meet two times. All right, and for them to at least meet, we know that the discriminant has to be greater than or equal to 0. So let me try to do that. So d has to be greater than or equal to 0. So this is the condition for the particles to at least meet, right? Okay, so if I set this here, that is going to be, v1 plus v2 square minus this is going to be greater than or equal to 0. Now, so let me try to rewrite that. v1 plus v2 square should be greater than or equal to then 2 a1 plus a2l. I have simply, used the value for d from here, right? If this is greater than or equal to 0, that means this has to be greater than or equal to this, right? Now, for a moment, for the time being, let's assume that a1 plus a2 is positive. So let's assume that this is a positive number. I'll discuss more about it a little bit later. But if that is positive, this tells me if I rearrange this, if I divide both sides by a1 plus a2 and also 2, then that tells me L is less than or equal to, I'm flipping it, there is v1 plus v2 square by 2 a1 plus a2, right? So what does this tell me? For the two particles to at least meet, the L has to satisfy this condition. L has to be less than or equal to this, right? And we are looking for the maximum value of L. If the L has to be less than or equal to this, the maximum value is going to be the equal to sign. So this tells me L max is going to be v1 plus v2 square over 2 a1 plus a2. Now this is exactly the expression we got earlier, right? So even if you started with, s is equal to ut plus half at square, we end up with the same expression. It is slightly longer way, and you have to think a little bit more in terms of, you are solving a quadratic equation, and you have to think a little differently, right? How you want to solve this. So it's not just solving straightforward like this. You are not trying to find the time, but from the discriminant of this quadratic equation, you are trying to infer what should be the L max. All right. From this point, actually, I want to go one more step ahead and give you some visual explanation based on this quadratic equation, and also explain why I need this a1 plus a2 to be positive. Remember, that's what I had assumed here. All right. So I have copied the quadratic equation here, and for simplicity, I'll just call this A and this V. So this is the two particle system. This particle 1, particle 2. And I'm going to represent the motion from the frame of reference of 2, right? So this is going to be V, this is going to be A, right? All right. So I have represented the two particle system where both the particles were moving. Now on 2 is at rest, so I'm representing this from the frame of reference of 2 where only 1 is moving. Okay, so now let me just copy few expressions from here. The d is v square minus 2al. D is v square minus 2al. Another thing is v square greater than equal to 2al. V square greater than equal to 2al, and this gave us L less than equal to v square by 2a. L less than equal to v square by 2a. So this was our final answer, right? So let me take this case first, a visual explanation of this case, because this is the easiest, and then we will look at the other ones later. So when this particle is the only one which is moving, and this is at rest, and this is the velocity and this is the acceleration, so it's going to go like this, like this, like this, eventually come to rest and going to come back, right? Now obviously it is going to go and come back in the same line, but I have drawn two different lines just to for visualization. Now this particle 2 can be anywhere. It can be here, it can be here, it can be here, it can be here, it can be anywhere, right? So if the particle was here, obviously it is not going to meet, right? If the particle is right about here, it's going to meet one time, and that is what gives us the value of L max. So this is the maximum separation, right? So this is going to be the L max, right? L max. At any other L, right, it is going to meet, there are going to be two solutions for time, right? So here, now what about this case? Now here, if you extend the particle motion to the past, not to the future, to the past, so the particle would be coming like this, the dotted line, and at this point we are assuming t is equal to 0, and it's coming back like this, right? So here there will be still two solutions for time, right? Because quadratic equation has two solutions. Remember, when the discriminant is greater than 0, then one represents to a negative time here. So this represents to a past time, which is a negative time, and this represents a future time. So this visually explains the our solution. Now I had said, assume that a is greater than 0. What happens if a is equal to 0? Then naturally, if a is equal to 0, this is not going to be a quadratic equation anymore, right? So the quadratic solution is not going to work. Instead, this is going to be linear solution. It's going to be negative v t plus L is equal to 0, and this tells me L is going to be vt, v times t, right? L is going to be v times t. Now this case, so the particle has no acceleration, so it is just going to continue going indefinitely, right? So there is no maximum value of L. Give me any L in the future, I can always, given enough time, I can always reach, right? So there is no maximum value of L. So this is the case for a is equal to 0. Next, let's see what happens if a was less than 0. All right. If a was less than 0, if I divide both sides by a again, right? So the inequality is going to flip, right? So v square by a. Now instead of greater than equal to, it is going to be less than equal to L. I also bring 2 to this side. So this is telling me L is greater than equal to v square by 2a. All right. So L is always going to be greater than or equal to v square by 2a. So there is no maximum value for L. There's a minimum value for L, but there is no maximum value. So this case, we can represent it like this. So this is the particle. So this is the first particle, right? Particle 1. Now, what is happening here? A is negative. What does A is negative means? The sign convention was that if this is V, this is positive A. If A is negative, that means the initial velocity is this way, and also the acceleration is this way. So here it will just keep accelerating, right? So it will just keep accelerating that side, right? But if we extend again the motion to the past, not to the future, to the past, this particle, so this is the dotted line, this particle, if I extend the motion to the past, would have come something like this. This is the past, and this is the time t is equal to 0 from where we are starting to examine it, and then it goes like this. It just accelerates away, right? Now, in this case, as you can see, again, there can be two time solution here, right? One, they can meet, the two particles can meet, one for the positive time, one at the negative time. And right about here, right, where L max is negative, in the past, like if in the imaginary case that the motion was extended to the past, they would have met at a minimum L max. So this is the minimum, right? This is the L where they meet will be always greater. There is no maximum value for L. There will be a minimum value for L from this equation, right? L has to be greater than equal to this. So L is always going to be greater than or equal to this. And there is a minimum value, and minimum value is this. So that is kind of the visual explanation for this. Again, so this requires a little bit thinking. So if you do not particularly get this slide, don't worry about it. If you understood the solution, that's good enough. All right, actually I have made some animations so that you can get a visual grasp of this problem. So let's discuss that. Remember, in the very first solution, I assumed that they come to rest when they meet, but that was a trap. So I'll show an animation showing that they don't actually have to come to rest when they meet. That's the first thing. And second thing is, we will see that from a relative frame of reference, it is easier to visualize this problem. And the third is, the discriminant value in the quadratic equation, right? We will try to see the different meanings of that, like when it is less than 0, equal to 0, and greater than 0. So let me start the animation. So see, so this is a special case. They come to rest when they meet, but again, this is the first solution. This is the special case. I'm showing another special case when this object is at rest and this just goes, meets, and comes back. Now let's look at this is the more general case. See, they meet here, but both the particles are moving, right? This is easier to see from the relative frame of reference. Here you can see I have the red as my frame of reference, and as you can see, let me do it again. From this frame of reference, this always comes, meets, and goes back, right? I'll show another example where they don't have to come to rest when they meet. See, is going and they meet here and both are still moving, right? But that is one point that they meet. Again, from a relative frame, it still meets and goes back. It's easier to visualize from a relative frame of reference. And then in this case, as you can see, let me just pause it for a moment. So here, so I have three cases, right? So in this case, the discriminant is less than 0. Here it is equal to 0, and here it is greater than 0. So in this case, since the discriminant is less than 0, those two particles, they are not going to meet. I'm going to replay the animation, we will see. In this case, you will see that they will meet at one point, right? And here you will see that they meet twice. They meet once here and once here. So let me replay that animation. No, it is this one. Okay, let me do it again. It is coming actually. Okay, it is this case. See here, they are not going to meet. They are not going to meet, right? I'll play that again. In the second case, they are just going to meet at one point here. And when the discriminant is greater than 0, there are going to be two solutions. They meet one time here and they again meet another time there. So this video is already uploaded in the YouTube. Feel free to play this video in slow motion and get a more comprehensive visual grasp of this problem. All right, so that was an animated explanation of this problem. Actually, one thing I forgot to mention, you might have already noticed, but for the case when the discriminant is 0 and they meet just one time, there is one solution for time, you might have noticed that when they meet, they do not cross, right? And when they meet, their relative velocity is 0, right? You feel free to go back and take a look at the animation again. But I thought I would mention that is an important point. Okay, so this is, on the surface, it's a very simple problem actually, but there can be some advanced framing of the same question. And the question may be, what is the condition on V1, V2, A1, A2 that there is a non-zero Lmax after they start? So there is a finite Lmax, non-zero, after they start the motion. The first part is easy. For it to be Lmax to be non-zero, V1 and V2, V1 plus V2 cannot be 0. That's straight from here, right? Because if V1 plus V2 is 0, then Lmax is going to be 0. The second point is the non-zero Lmax after they start. So if you go back here, you can see that in this case, right, there is a non-zero Lmax after they start. But for this case, when A is equal to 0 or when A is less than 0, there is no value of Lmax after they start, right? So that's what it is here. So this condition is going to be, first, that A1 plus A2, it cannot be 0. And the second condition is A1 plus A2, same sign as V1 plus V2. Now, this is because of our sign convention, right? So if I take the motion of the first particle, so I'm looking from the frame of reference of 2. So this is going to be V, this is going to be A. So what does it mean by A1 plus A2 have the same sign as V1 plus V2? That means in reality they are in the opposite direction, right? That's how our sign convention is. If V is positive this way, I'm assuming A is positive this way, and they have to be directed in the opposite direction to be able to find a non-zero Lmax after they start. All right, there are some final remarks on this problem. We have already discussed some of the points, but just to reinforce, the first thing is Lmax to meet is same as saying Lmin that they don't meet. So the problem said find the Lmax that they are going to meet, which is same as saying find the minimum separation that they do not meet. It's the same thing. The solution does not require v1 a1 v2 a2 to be positive, right? We also saw that in animations they can have positive or negative signs. They are just some symbols, but the numerical values can be positive or negative, right? The relative frame is easier to analyze for this problem. We also saw that in animation, and I also highlighted this point earlier. When they just meet without crossing, the relative velocity must be zero, right? But the individual velocities are not necessarily zero. They can be still moving. Okay, the last is, if you avoid the traps, you can solve this problem in less than 10 seconds, right? So on the surface, it's a very easy problem, but there are few traps for this problem. So if you avoid those and if you get the right idea from the get-go, you can really solve it quickly. So basically, important thing is practice, right? I have also some general remarks. Keep in mind the inherent assumptions you make while using a formula. Remember, in the very first solution, I used v square minus u square is equal to 2as, and then I equated the distances, the s1 max and s2 max, and said that that is L max. So by doing that, I inherently assume that they are going to meet at the same time, but that is not necessarily true. That was a trap, right? The second thing is, uh, be careful with sign conventions. Avoid silly mistakes. In the second solution that I got, the relative velocity, I wrote v1 2 is equal to v1 minus v2. So that was a very silly mistake. That was another trap. I forgot that v1 and v2 are in the opposite direction. Okay, so be careful with the sign convention. Now listen to the whispers of expression. So this is the most important thing actually. If you get used to doing this or get into the habit of listening to the whispers of expressions, actually you can catch these mistakes, right? um Now, another point is, inferring solution from a quadratic equation is not always straightforward. It's not that when you have a quadratic equation, you always solve for that the variable. It's sometimes you have to look at the discriminant and infer the solution. And the last point is, during the exam, you will be under the time pressure, right? So it is not, you are not going to always get the most efficient or the best approach all the time, right? So sometimes, you know you will take a different path, but no matter what, you should be able to arrive at the solution. And for that, it is really important to practice multiple approaches. And actually, if you do practice multiple approaches under the time pressure, it will be more likely that you will remember the best approach. All right, so that is it for this problem. I hope you liked it. Thank you, and I will see you in the next video.